In this video, we'll go through how to calculate surface integrals and look at a few examples. From our last video, we learned that the surface integral of a function g over the surface S, defined by z equals f of xy on a region R on the xy plane, is denoted as the double integral over S of g ds. And we calculate a surface integral by doing a double integral over the region R of g times the square root of the partial derivative of f with respect to x squared plus the partial derivative of f with respect to y squared plus 1. Now let's go through some examples to see how we calculate the surface integral. So here we want to calculate the surface integral of x plus y plus z ds, where s is the portion of the plane 2x plus y plus 4z equals 4 in the first octant. To begin, we have the following picture for our surface. Find how the plane intersects each of the coordinate axes by setting the appropriate variables equal to 0. For example, if I want to find how it intersects the x-axis, I set y and z equal to 0. That leaves me with 2x equals 4 or x equals 2. So I know that my plane intersects the x-axis at 2, 0, 0. Similarly, you can find that the plane intersects the y-axis at 0, 4, 0, and it intersects the z-axis at 0, 0, 1. Now if I want to calculate my surface integral, I would need to describe my surface in the form z equals some function of x and y. Also, I would need to describe the region R on the xy plane that my surface is over. Since my plane is defined by 2x plus y plus 4z equals 4, I can solve for z to get z equals 4 minus 2x minus y all over 4. Now to figure out the region R that my surface is over, I would need to project my surface onto the xy plane. If I want to do a double integral over the region R, I would need to pick an order of integration. I can do it dy dx or dx dy. In this particular region, it doesn't really matter, so I'll pick dy dx. So I'm going to draw vertical lines through my region, and we see the vertical lines are bounded above by my line and bounded below by the x-axis. Now I can find the equation of the line by setting z equal to 0 in the equation for my plane. By doing that, I'm intersecting my surface with the xy plane. So when I set z equal to 0, I'm left with 2x plus y equals 4, which I can solve for y to get y equals 4 minus 2x. So that's the upper bound for my y. My lower bound for the y is the x-axis, y equals 0. And finally, I know that my region goes from x equals 0 to x equals 2. So now I'm ready to set up my double integral. So my surface integral, which is the double integral over S of x plus y plus z ds, can be computed as the double integral of x plus y, and then the z I'm going to replace with 4 minus 2x minus y over 4. All of this times the square root of fx squared plus fy squared plus 1. Now f is this function right here. So fx is negative 1/2 squared plus fy is negative 1/4 squared plus 1, and then dy dx. My y's are bounded from 0 to 4 minus 2x, and my x's are bounded from 0 to 2. This simplifies as the double integral from 0 to 2, from 0 to 4 minus 2x of 1/2 x plus 3/4 y plus 1 times the square root of 21 over 16 dy dx. I won't go through the details of this double integral, but in the end you should end up with 7 root 7/3. Let's go through one more example. So here we're asked to find the mass of the portion of the paraboloid z equals x squared plus y squared under the plane z equals 1 if its density at any point is given by the density function rho equals z squared. So here we have a picture of our paraboloid. So to find the mass of this object, I would need to do the surface integral of the density function over my paraboloid. So here my surface is z equals x squared plus y squared. What I need to do is determine the region R on the xy plane that my surface is over. If I take my paraboloid and project it down onto the xy plane, Here is the picture that I would see. Now, to figure out how this region is defined, well, I would need to think about what the widest part of this paraboloid is. It's where the paraboloid z equals x squared plus y squared intersects the plane z equals 1. So the widest part of this paraboloid is the intersection of those two equations, which is x squared plus y squared equals 1. So when I project this down, I'm looking at the region within the unit circle x squared plus y squared equals 1. If I want to do a double integral over this region, I would probably do it in polar coordinates. So I can describe my region as r values between 0 and 1 and thetas between 0 and 2 pi. Now I'm ready to set up my surface integral. I'm looking at the surface integral over S of the density function rho ds. That's going to be the double integral of the density function z squared, but I'm going to replace the z with x squared plus y squared. So z squared is now x squared plus y squared squared. And then I want to multiply by square root of fx squared plus fy squared plus 1. In this problem, f is x squared plus y squared. So I have the square root of fx is 2x. So that's 2x squared plus fy, that's going to be 2y squared plus 1 dA. And I'm integrating over the region R. This here simplifies to the double integral over R of x squared plus y squared squared times square root of 4x squared plus y squared plus 1 dA. Now if I write this double integral in polar coordinates, I have the integral of x squared plus y squared gets replaced with r squared. So I have r squared squared times square root of 4r squared plus 1. And then dA, we need an r dr d theta. My r values go from 0 to 1, and my thetas go from 0 to 2 pi. So we have the integral from 0 to 2 pi, integral from 0 to 1 of r to the 5th times square root of 4r squared plus 1 dr d theta. This double integral you can compute using substitution, but I won't go through the details here. In the end, you should get that the mass of the paraboloid is about 2.083. So that's it for this video. In our next video, we'll look at surface integrals involving vector fields and something called flux.